Okay, we're about to start chapter 25 and talk about electrical current. Just to really get us started with the basics, I'm going to do a couple short videos on the definition of electrical current, the definition of resistance, how to use Ohm's law, and that'll set us up for some of the more complicated circuit stuff that is coming up. So the first thing your book does in chapter 25 is it defines the notion of electrical current in terms of an amount of electrical charge flowing through either a surface or past some point in a particular time. So if you've got, say, a wire with a cross-sectional area, we define the electrical current as the amount of charge that flows through that area in a particular time, delta t. And if we want to define that in terms of calculus, we write that the current is equal to dq dt, where the q represents the amount of charge flowing through a cross-sectional area. We're going to assume when we're talking about electrical current, just like we did when we talked about fluid flow, that the rate of flow of the current is constant. We're taking an average. It might be true that the rate that electrons are moving at the edge of a wire and the center of a wire are not the same. We take the total charge flowing through a wire over time, and we call that the current, and we leave out any kind of microscopic considerations of what's happening to individual electrical charges at the microscopic level. When we first defined electrical current back in the 1700s, well, actually, let me back up just one second here, and make sure we are clear on a couple of things. First of all, if electrical current is the amount of electrical charge that flows per unit time, that means that the units of electrical current are going to be in coulombs per second. And we give that unit a definition called the ampere. So an ampere, or amp for short, is a unit of electrical current, and it is a SI standard unit based on the coulomb and the second. An amp is a lot of current. So we will often, if we're dealing with electrical circuits with like batteries and light bulbs and stuff, be dealing with milliamps and maybe even microamps, thousandths or millionths of an amp of current. Back in the 1700s, when people first started messing around with electrical circuits and stuff, we didn't really know what the thing was that was moving around in an electrical circuit. And the names, the labels for charges that we use, positive and negative, are essentially arbitrary labels that have been in use for hundreds of years. It turns out that when we decided to define the idea of electrical current, we defined current as going from the positive terminal of a battery. If we've got a battery, just a regular 1.5 volt C or D battery, like you might put in a appliance in your house, we define the direction of current flow from the positive terminal to the negative terminal. That is, current is defined as the direction of flow of positive charge, dq dt. It wasn't until the very late 1800s, 1897, I think, that we discovered that there are these little particles called electrons, and these little particles called electrons are the things that are moving in an electrical circuit, and those things have a negative charge. So in an actual electrical circuit, if you connect the positive terminal of a battery with a wire to the negative terminal of a battery, what happens in that wire is that electrons are repelled from the negative terminal and attracted to the positive terminal, and electrons flow in this direction around the circuit. Regardless, we still call current, the direction of current in a circuit, by convention, from the positive potential to the negative potential, or from the plus voltage to the negative voltage. So when we draw an electrical circuit, and I'll go through these diagrams in a separate video, the direction of the thing we call current goes from positive around the circuit to negative, despite the fact that the actual electrons in that circuit are moving in the opposite direction. If you want to think about it algebraically, if current is dq dt, the charge of electrons is negative. So the direction of the electron flow is opposite the direction of what we call, or what your book calls in this instance, the conventional current. So it's just something to always keep in the back of your head, that when we talk about current in electrical circuits, the direction of that quote-unquote conventional current from positive to negative is not the direction that actual electrons are moving in the wire. When we invented this convention in the 17 and the 1800s, we didn't know that the structure of matter is such that the protons and things in the nucleus basically stay put when you've got a solid piece of matter, and the electrons are the things in a conductor that are free to move. So essentially we got the convention wrong, but by then it was too late to change it. So we're kind of stuck with this weird situation where the direction of the current and the direction of the electrons are opposite. The relationship between potential difference and current is relatively simple and linear. The person who discovered that this was linear was a fellow by the name of Georg Ohm back in the early 1800s, 1827, and he discovered that if you have a source of electrical potential, that the current is proportional to the voltage, or the electrical potential difference between 2 points in that circuit. And from that relationship, we get the rule that the potential V is proportional to the current I, and that constant of proportionality we call the resistance, or R. And this law is known as Ohm's law. It's one of the most straightforward laws of physics, probably second only to Newton's second law in terms of being very, very easy to write down. It's just a linear proportionality. You can actually think of Ohm's law as being the definition of resistance, just like you can think of Newton's second law as being the definition of mass. Mass is that thing that resists acceleration in Newton's second law. Resistance is that thing that resists the flow of current in Ohm's law. And just like Newton's law, solving simple problems with Ohm's law is very straightforward, but you can make those problems more and more and more complicated, which is what we will do over the next week or so. Your book had an example. I thought I pasted an example in here from the book where you're just asked to find the current given the resistance. Let me really quickly, since I've already started recording this, copy and paste a problem from your book, which asks, suppose you've got a flashlight. Where'd that problem go? Here we go. Suppose you've got a flashlight and you know the voltage of the battery. Here we go. And you know the, what do you know in this case? You know the current. So this is example 25-4 in your book. You've got a small flashlight with a 1.5 volt battery, which is the voltage of most C, D, AA, AAA batteries. And the current flowing through the light bulb of the battery is 300 milliamps. And the question is just, what is the resistance of the bulb? And that's a simple linear relationship. The voltage is equal to the current times the resistance. So the resistance is equal to the voltage divided by the current, which is 1.5 volts divided by 300 milliamps. So that's 0.3 amps. Right? 300 milliamps is 300 thousandths of an amp, and 1.5 over 0.3 is the same as 15 over 3, or 5 5 what? 5 volts per amp. We don't go around writing volts per amp when we write resistances. We, in fact, have created a new unit named after Mr. Georg Ohm and his Ohm's law, and we use the symbol omega, and the unit for resistance is the ohm. So that's 5 ohms, and the unit 1 ohm is defined to be a volt per amp. So really, really straightforward linear equation that is essentially an empirical equation. In other words, Georg Ohm discovered this by putting different amounts of batteries in an electrical circuit and measuring the resulting current. I want to talk a little bit, having defined resistance, about the sort of microscopic meaning of resistance. But before we do that, since we're going to be drawing some electrical circuit diagrams, I want to do a really quick video on just the symbols that we use to draw an electrical circuit, and then we'll continue on talking about resistance.